let's quickly look over some properties of eigenvalues that might be useful later on in this course. Okay, so recall if we've got A is a n by n matrix, then eigenvector is some vector E that when we apply A to it, we simply get E back after it's been scaled by some scalar quantity lambda. So lambda is the eigenvector of A associated with eigenvalue of A, associated with the eigenvector E. Now we've seen that any eigenvalue of A satisfies the equation A minus lambda I, so the determinant of that thing equals 0. Okay, so and that's known as the characteristic equation, and if we expand this thing out, that's the characteristic polynomial of A. Now this is a polynomial of degree n, and so it has n roots, lambda 1, lambda 2, up to lambda n. Okay, now we can say that for certain special matrices, we can say something about the eigenvectors. In particular, when A is symmetric, right? So when A equals A transpose, then there's a full set of n orthogonal eigenvectors, right? So when A is symmetric, n orthogonal eigenvectors. How do we find these things? Well, we saw that we could find the eigenvalues as the roots of this polynomial, but that polynomial is large, and if we're dealing with n greater than 4, then finding those roots can be very hard. There's no algebraic formula for finding the polynomial roots finding the roots of a polynomial when it's of degree 5 or more. Okay, there are a couple of tricks we can use. If we know some of the eigenvalues, we can find the remainder. So there's a result that says that the determinant of A is equal to the product of the eigenvalues of A. Right? So lambda 1 times lambda 2 times lambda n. Right? So if we can quickly figure out the determinant of A, and we know all but one of the eigenvalues, then we can find the remaining eigenvalue. Another similar result is that the trace of A, right, which is the sum of the diagonal elements of A, okay, so that's the sum of I equals 1 to n AII, right, so A11 plus A22 plus and so on up to ANN, that is equal to the sum of the eigenvalues of A, right? So if we sum I equals 1 to n lambda I, equals lambda 1 plus so on up to lambda. Okay, so now suppose we know the eigenvectors of A and the eigenvalues of A. So the eigenvalues are lambda 1 to lambda n, and the eigenvectors are E1 to En. What can we say about the eigenvalues and eigenvectors of related matrices? So let's start by looking at the transpose. Well, it's easy to show that the eigenvalues of the transpose are exactly the same as the eigenvalues of the matrix itself. So the eigenvalues of AT are just a lambda 1 up to lambda n. The eigenvectors are, well, we can't actually say anything about those in the general case. So even if you know all the eigenvectors of A, unless A has a very special structure like it's symmetric, we can't say anything about the eigenvectors of A transpose. How about if we raise A to the kth power, right? So we apply A to some vector, say k times A to the k, right? So that equals A times A times A, k times. Well, the eigenvectors remain the same as they are for A. So E1, E2 up to En. The eigenvalues, well, think of how the eigenvalues work. They stretch, each time we apply A, an eigenvalue is stretched by some amount lambda. So if we apply, say, A to E1 k times, then it's going to stretch E1 lambda 1 to the power of k times. In other words, the eigenvalues of A to the power of k are just the eigenvalues of A, each raised to the power of k. And finally, let's look at the eigenvalues and eigenvectors of the inverse matrix, right? So let's assume that inverse matrix exists. Then the eigenvectors, again, are just the same as the original matrix. And the eigenvalues, well, instead of stretching k by some amount, lambda 1, for example, it shrinks it by amount lambda 1. So, in other words, the eigenvalues are just the inverse of the eigenvalues lambda 1 to lambda n. And notice that the eigenvalues, none of these eigenvalues are 0. And we know that because we've assumed that A inverse exists, right? So the determinant is non-zero. And remember, the determinant is equal to the product of the eigenvalues. Okay, let's look at a quick example. So if we have that matrix A equals 2 minus 1 minus 1, 2, then the first thing we notice about this matrix is that it's symmetric. In other words, A transpose equals A. So let's find the eigenvalues of this matrix and then see how we can find easily the eigenvalues and eigenvectors of related matrices and check some of the properties of those eigenvalues. Okay, so the eigenvalues of this are found as the solution to A minus lambda I, the determinant of that thing equals 0. So that's equivalent to solving this characteristic polynomial, which, so what's that going to look like? We'll get 2 minus lambda minus 1 minus 1, 2 minus lambda equals 0. And that is equivalent to, after a little bit of rearranging, we get lambda minus 1, lambda minus 3 equals 0. So our eigenvalues must be lambda 1 equals 1, lambda 2 equals 3. Okay, and we're not going to derive what the eigenvectors associated with these eigenvalues are. That's in the notes if you want to see it. But it's easy to see that E1 equals 1, 1, and we choose a length so that the thing has length 1, right? And E2 equals similarly 1 over root 2, 1 minus 1. Okay, so let's check then that some of the results we saw earlier hold. So A was 2 minus 1 minus 1, 2. Our eigenvalues were lambda equals 1 and 3, right? So we saw that we expect the trace of A, which is, so that's A11 plus A22 in this case, which is just 2 plus 2, which equals 4. Note that that's the same as the sum of the eigenvalues. Lambda 1 plus lambda 2 equals 4 also. The determinant of A is just, what is it? It's 2 times 2 minus minus 1 times minus 1, which is 4 minus 1, which is 3, and indeed that equals 3 times 1, which is lambda 1 times lambda 2. Okay, so that result holds, obviously. The inverse of A, so it's just a 2 by 2 matrix, so A inverse looks like 1 over the determinant, so 1 over 3, then 2, 2, 1, 1, right? And we don't need to directly work out what the eigenvalues of that matrix are, because we know what they are of A. So the eigenvalues of this inverse matrix are going to be lambda 1 equals 1 over 1, so that's 1, and lambda 2 is just going to be 1 over 3, and we leave it at that. Okay. Finally, if we look at the matrix A squared, right, so it's 2 minus 1 minus 1, 2 times 2 minus 1 minus 1, 2. So that equals, what does that equal? 4 plus 1, what is it? Minus 4, oh sorry, minus 4, minus 4, 5, right? Again, we could go through the rigmarole of directly calculating the eigenvalues of this matrix, but we can simply say that that's just two applications of A. So lambda 1 is just going to be 1 squared, which will be 1, and lambda 2 is 3 squared, which is 9. Okay, and similarly we could do that for any power of k.